Good morning, children. Today we'll discuss about radiation pattern. Let us go with the presentation. Radiation pattern. So let us discuss about the radiation pattern. Now, if you consider any antenna, so any antenna cannot radiate the energy with the same strength uniformly in all the directions. Why? Because in particular direction, the energy may be radiated large, but in the case of another direction, remaining directions, it may be zero or it may be minimum in remaining all the directions. That means antenna can radiate only in a particular direction with a large amount of energy, and remaining all those directions, it may be zero or it may be minimum radiation it can be propagate. So here the radiation from any antenna in a direction is measured in terms of field strength at a particular point. So how can we measure the field strength? So here the field strength can be calculated by measuring voltages at any 2 points on an electric lines of force, and then by dividing the distance between 2 points we'll obtain the field strength. So here unit of radiation pattern is volt per meter. Generally the field strength is expressed in millivolts per meter. The radiation pattern of an antenna is the important characteristics of the antenna because it indicates the distribution of the energy radiated by an antenna in the space. So here, in generally, if we consider the radiation pattern, what is radiation pattern? The name itself we have pattern, that means which is a graphical representation. So here, radiation pattern is nothing but a graph which shows the variation of the actual field strength of the electromagnetic field at all the particular points, which is equidistant from the antenna. So here, the radiation pattern, it is a three-dimensional graph. So here we have two basic radiation patterns. If the radiation of the antenna is represented graphically as a function of direction, it is called radiation pattern. But if the radiation of the antenna is expressed in terms of field strength E in volts per meter, then the graphical representation is called field strength pattern or field radiation pattern. And second one, if the radiation of the antenna is expressed in terms of power per unit solid angle, then the graphical representation is called power radiation pattern or simply power pattern. Radiation pattern is nothing but it is a 3D graphical representation of the field strength. Now, directional and omnidirectional patterns. Already we have discussed here. What is a radiator? Here, when a radiator acting as a lossless hypothetical antenna radiating equally in all the directions is called isotropic radiator. That means here, in generally, practically, it is very impossible. That means any antenna cannot distribute the radiation with lossless or hypothetical. So that's why it is an ideal concept which is hypothetical and cannot be realized practically. In the case of isotropic radiator, which the radiator acts as a lossless hypothetical antenna. And here, if you discuss an antenna with a property of radiating or receiving the electromagnetic waves more effectively in some directions than in other directions is called directional antenna. That means if you consider any antenna, it has a property of radiating or receiving the electromagnetic waves. And here, when the antenna which radiates or receives the electromagnetic waves more effectively in some directions than in other directions is called directional. And that means the antenna, the radiation can be propagated only in a particular direction is called directional antenna. So the direction pattern of such antenna is called directional pattern. So when antenna has maximum directivity greater than that of the half wave dipole is known as directional antenna. And another one here, the pattern discussed above is called directional pattern because the pattern is directional in elevation plane but non-directional in azimuth plane. Such a pattern is generally called omnidirectional pattern. That means what is omnidirectional pattern? It is defined as the pattern which is non-directional in a given plane while directional in any orthogonal. Orthogonal means any 90 degrees plane. That means omnidirectional pattern is nothing but pattern which is non-directional in a particular given plane while directional in any orthogonal plane. So omnidirectional pattern is a special case of a directional pattern. Now let us consider field radiation pattern. So here the complete field radiation pattern here we can discuss by using three-dimensional pattern, and it requires a three-dimensional representations to represent the radiation for all the angles, that means phi and theta. So a complete 3D dimensional field. Here, this is the representation. Here we can observe here, and this is the main lobe, and here back lobes which are opposite to the main lobe, and here these are the side lobes, and here these are nulls, and here these are. So in the case of main lobe only, the radiation can be propagated in a more effectively here. But in the case of nulls or backlobes, so the radiation it is propagated, it is almost negligible here. And here this is P, which we can find out the potential here, field in theta comma phi direction. And here these are the E theta and E phi, these are the electric field components in theta and phi components. And here this is the y direction, and this is phi dash, and here in x direction, here phi equals to 0, and this is the principal direction, theta is equals to 0. So this is the three-dimensional representation of field radiation pattern of an antenna. This is, so from this lobe, the antenna can be radiate effectively in particular direction. And here already we have discussed, and now let us see this one. So the field radiation pattern can be described completely with respect to the field intensity and polarization using the following three important factors. So here we have, so E theta, E phi, and the phase angles delta theta, delta phi, and E theta, theta gamma phi, which is the theta component of the electric field as a function of angles theta and phi, which can be expressed in volt per meter, and E phi component, and which as a function of theta and phi expressed in volts per meter. And here this is the phase angles as a function of here theta comma phi, the field components expressed either in degrees or radians. And here generally the field pattern can be expressed mathematically in terms of relative field pattern, which is commonly called normalized field pattern. So the normalized field pattern is defined as, what is normalized field pattern? The ratio of field component to its maximum value. Basically, normalized field pattern which is a dimensionless quantity with maximum value which is equals to 1, that means unity. So these normalized field patterns, theta and phi components of the electric fields are given below. So here the normalized field pattern, so ratio of field component to the maximum value. So normalized field components ratio of here this is ratio of here we can observe here normalized field pattern, which is here basically normalized field pattern, it is a ratio of the field component to the maximum value. And here field component E theta, theta comma phi, this is the maximum value of the field component. So this is the normalized here and represents here normalized. So he E theta and theta comma phi, which is equals to E theta, theta comma phi by E theta, theta comma phi maximum. Similarly, so E phi n normalized component here theta comma phi equals to E phi into E phi of theta comma phi by E phi theta comma phi maximum. So here the shape of the field radiation pattern is independent of distance r, where it is larger than the antenna maximum dimension to the wavelength. So it is unusual practice to find the field radiation patterns for the far field conditions only. So here already we have seen, so as a three-dimensional pattern cannot be plotted in a plane. So in a plane we can plot only two-dimensional. So three-dimensional cannot be plotted in a plane. So three-dimensional representation is avoided. So instead of this, the polar plots of the relative magnitude of the field in any desired plane are sketched. So these polar plots are plotted in two planes, namely one containing the antenna and other the normal to it. So these planes are called principal planes, and the two plots or patterns are called principal plane patterns, and these patterns are obtained by plotting the magnitude of the normalized field strength and the magnitude that when the normalized field strength is plotted versus theta with constant phi. So the pattern is called E plane pattern. Let us see here. So here these are the E plane pattern, and this is H plane pattern, and here we can observe here phi is constant. Here in this pattern phi is and here it is E plane, here phi is constant, and here theta is varying, but here theta equals to pi by 2, which is constant. Here phi is varying, and here theta is varying, and here theta equals to pi by 2, which is constant, which is the horizontal plane and or H plane, and this is E plane or vertical plane. So here This is the normalized field, normalized field strength versus theta with constant phi. So here in this diagram we can observe the constant phi, and here we can observe the phi varies, and already we have seen. So here the radiation pattern gets changed if the length of the dipole is increased. So when the length of dipole is increased, radiation pattern is get changed. So here for a center fed half wave vertical dipole, radiation pattern is also shown in the diagram. So here field radiation pattern for vertical dipoles and half and one wavelength. Here this is for half wavelength and this is for one wavelength. And here we can observe here this is half wavelength and this is for one wavelength. Radiation pattern. So this is the radiation pattern for one wavelength long, and here it is vertical dipole. And here the field radiation pattern for 1.5 wavelength and 2 wavelength vertical dipoles are shown here for 1.5 wavelength, and this is for 2 wavelength. Field radiation patterns. This is the graphical representation, 2D graphical representation, field representation pattern for vertical dipoles. And here this is 1.5 wave, this is 1.5 wavelength, and this is for 2 wavelength. Now already this is completed, and now let us see power radiation pattern. So here when the radiation is given in a direction which is expressed in terms of power per unit solid angle, the pattern is called power radiation pattern. What is power radiation pattern? The radiation in a given direction is expressed in terms of power per unit solid angle. The pattern is called power radiation pattern. Again, consider it again here also. Let us consider a spherical surface with radius r centered at the point P, source representing the antenna. So at a particular point on this surface, the radiated power flows radially outwards. So the corresponding electric and magnetic fields are normal to this direction and are also mutually perpendicular with E by H equals to 125 for free space. So here the power density, which is represented with suffix d. Power density theta comma phi is defined as power flow per unit area and is a function of the direction theta comma phi. The power density can be expressed in terms of magnitude of the electric field intensity is given as, so power density theta comma phi equals to half E theta comma phi whole square by eta naught, which can be written as half E theta comma phi whole square by 120 pi. That means here eta naught equals to here 60, 60 pi. No, 125. Eta naught is equals to here 125. So watts per square meter. So where E theta comma phi is equals to square root of E theta square theta comma phi plus E phi theta comma phi whole square, and eta naught which is equals to 120 pi omega here. So intrinsic impedance of the free space. So the direction in which E theta comma phi is maximum, power density is also maximum, and it is denoted by PD theta comma maximum. Now similar to the field radiation pattern, mathematically power radiation pattern is represented in terms of its normalized value denoted as PDN theta comma phi. That means here power radiation pattern in terms of normalized value. Again here we can write suffix n here, PDN theta comma phi, which is equals to power density theta comma phi by power density maximum theta comma phi maximum, which is equals to E theta comma phi whole square by E theta comma phi maximum, which is equals to Fn square theta comma phi. So here P dn theta comma phi, it is a normalized power radiation pattern, and it is also independent of distance r measured from the origin to the distance point P. Since power density theta comma phi and power density theta comma phi maximum both vary inversely with r, the power radiation pattern is plotted similar to the field radiation pattern. So for example, if the field radiation pattern is given by f theta comma phi equals to sin theta, then power radiation pattern is given by PDN theta comma phi equals to f square theta comma phi equals to sin square theta. Generally, the power radiation pattern is also represented as a two-dimensional sketch. For Hertzian dipole with constant phi, the power radiation pattern are also shown in already. We have seen like this. So like this we can plot. So like this we can plot the. So like that power radiation pattern also we can plot like that. Thank you, children.